The cloud. All right, awesome. So today we are going over discussion number 7. So we have 7 and 8 before our next exam. So we'll have this one more next week, and then the exam is the following week. So the exam is 2 weeks from today already. But I think that's going to be good because that's only, 2 weeks of material on the exam. So it won't be like you have to study as much as you did for unit 1. I think y'all are in the 8 a.m. lecture, correct? Okay, so I don't know what y'all's average was, but the 9:30 a.m. average was a 78, so definitely a huge increase from the last exam, which was a 55. So congratulations, y'all are obviously learning how to study better. I was really impressed as I was grading the short answers and all of that. I know I didn't get to grade y'all's, but I'm sure the trend was pretty even throughout the entire classes, but yeah. So again, if you want to review your exam, schedule it with the UGTAs and make sure it's the UGTAs for the lecture you're in. So sometimes the 8 a.m. Because I'm y'all's TA for discussion, y'all will email me to review the exams, but make sure you review the exams with the UGTAs in the 8 a.m. lecture. But yeah, any other announcements? I don't think so. Do y'all have any questions? Yeah.
I think I know the answer to this. I think it's no. Like, is there any curve at the end of this?
Yeah, no. So for sure, there. So how he does it is, I think it's either an 82 or an 85. If it's like, if the class average, like all of y'all's final scores, is like a 72, he'll curve that up to like an 85 somehow. So I'm not super.
Based on your final.
Exactly. So he wants the class average to have like the score of either an 82 or an 85. And so however many points it takes it to get to that point is how many y'all will be added. But from what I've heard is there's a curve every semester. So that is promising, but yeah. But no exam by exam curve, just that overall curve. So but yeah, good question. I thought a lot of people are wondering that. Anything else? Okay. Cool. Well, let's hop on into it. So today we're going over the beginning of the cardiovascular system. So we're looking at EKGs, electrocardiograms. I said EKG, it's also known as ECG. The term came from a Russian scientist, and in Russia, the cardio part started with a K, so that's why we normally call it EKG instead of ECG, but all the same thing. So you can use those terms synonymously. So before we hop on in, I kind of wanted to just go over an electrical review of the anatomy of the heart. So we're just going to kind of briefly look at just kind of how electrical currents travel through the anatomy of the heart. This isn't on your discussion worksheet, but I think it's really helpful to know to begin the worksheet. So what happens is, in the right atrium, we have the SA node. You can see it, it's like that little dot right there. And that's what we call the pacemaker of the heart. So it sets the beat. It decides how fast, how slow, and the rhythm of our heartbeat. So what we see is that the SA node will depolarize. And when it depolarizes, it's going to send that depolarization down these internodal pathways. They're like these fibers that travel throughout the atrium and meet up at the AV node. So the AV node is right here. So SA node, AV node. The AV node will have a slight delay from the time that depolarization reaches it. So we'll have this little small delay. And then once that AV node depolarizes, it will spread that depolarization down the septum of the heart, and it'll meet down here at the at the apex. So the apex is this point at the heart, kind of like the left corner, and extending upwards from the apex, we have the Purkinje fibers. And those Purkinje fibers are what actually innervate the ventricles and cause them to contract. So the ventricles, again, send blood to the entire body. The atrium send blood to the ventricles right downstairs, but the ventricles have to pump blood all the way to the top of our head, to our fingertips, and down to our toes. So the ventricles contraction is really important. And again, those Purkinje fibers are what is going to innervate those ventricular muscles to cause that beat. So yeah, that's kind of just this 1, 2, 3, 4, 5 step process of conducting electricity through the heart. We're going to get into the actual voltage and all of that today, but I think this is a good overview to kind of understand, the gist of what's going on. But yeah, all right. So if you want to draw this out, what we're going to be doing is kind of labeling the difference between autorhythmic action potentials and the contractile cell action potentials. So this again is not on your discussion worksheet, but it's going to be really helpful to know this as we work through it. So if you want to draw out this chart, and if you need scratch paper, let me know. I do have some. We're going to be drawing 2 different charts today. So begin with this one. So let's go ahead and hop on into it. So one thing that we see about autorhythmic cells, which just so you know, the autorhythmic cells are right up here in the SA node, and the contractile cells, which we'll be looking at next, are throughout the heart muscle. But the autorhythmic cells are the cells in the SA node that are going to cause that rhythm. So what we see is that these guys have no resting membrane potential. It'll kind of just depolarize naturally. So they don't really sit at rest. Like it's kind of always, it's not like always going to be -60. They don't really have this resting potential, and they don't really have like this trigger to be stimulated. It just depolarizes naturally. So what we see is that depolarization is caused by the opening of funny channels. And that's not like a mnemonic or anything. That's what they're actually called, funny channels, sometimes abbreviated IF. And what happens, or what those are hyperpolarized gated channels. They're like a form of voltage gated channels, but they don't really act like the ones that we've seen so far. Instead, they kind of respond to hyperpolarization. So what we see is that these funny channels are going to act kind of as like those nicotinic acetylcholine channels. So they're kind of acting like a non-specific cation channel. So what happens is when those funny channels open, we're going to have sodium influx and potassium efflux or outflow. And that's going to cause that slow rise in voltage. So this is kind of what we call slow depolarization. It's slowly coming up. We have not met threshold yet, but that's, we're rising in voltage due to those funny channels opening, sodium coming in, potassium flowing out. And again, we can call that slow depolarization. But if you see, there's a little mark before we hit that threshold. And what happens there is voltage gated calcium channels are going to open. And when those open, the cell is going to be filled, or calcium will flow in, and we will have fast depolarization. So this is our fast depolarization, that rapid rise in voltage becoming more positive. And that's due to those voltage gated channels opening and calcium flowing into the cell. So slow depolarization is this point before threshold. Fast depolarization is once those calcium channels open. So at this point right here, what's going on is those voltage gated channels close, or voltage gated calcium channels close, and voltage gated potassium channels open. So these close, the ones that we opened down here, and then we're going to reopen these potassium channels. When we do that, we're going to have repolarization due to that potassium flowing out of the cell. So the repolarization is due to that potassium efflux, just like when we looked at the neuron action potential. And then this will repeat and send signals to the contractile cells that we will look at next. But the main difference here that's to be noted is with regular action potentials of the neurons that we've studied so far, this depolarization was due to sodium influx. But when looking at the autorhythmic cells, it's going to be due to a calcium influx. So make sure you don't confuse the neuronal action potentials where sodium rushes in and that causes the fast depolarization. We do have sodium influx down here, just not at like a really quick and like large level. The potassium efflux is the same though. All right, any questions there? Cool. All right, so overall what this is showing us is the cardiac cycle in terms of electrical activity of the heart. So as we work through our worksheets today, we'll be looking at the cardiac cycle, and this will be a good reference. Something really important to note is the heart needs no neuronal influence to beat. We do not need any type of signal or release of neurotransmitters for it to beat. We can have neuronal influences via the SNS and PSNS. So like the SNS can speed up heart rate by, sending neurotransmitters like adrenaline, epinephrine, norepinephrine. The PSNS can send other neurotransmitters to slow it down, but those aren't necessary for the heart to contract. We don't need those neuronal influences or those neurotransmitters to do it. It's just going to naturally depolarize on its own. All right, cool. All right, so this is going to be our second chart. So if you want to go ahead and draw this out, we will start hopping on into it. And note that there is no threshold line here, so don't draw a threshold line. All right. Okay, so this is looking at that should have said contractile action potential, but this is looking at our contractile cells. So again, those autorhythmic, we're in the SA node because that's our pacemaker, our rhythm decider. And once that action potential ends that we just saw, it's going to send this signal to the contractile cells, which will actually cause this contraction. So what we see is that the contractile cells do have a resting potential, which is negative 90 millivolts. So they do sit at rest. And what we see is that they don't need to cross a membrane threshold to depolarize. Instead, they'll just be signaled from those autorhythmic cells. So the autorhythmic cells hit that threshold, and then we have that fast depolarization. Here, once they're signaled by the autorhythmic cells, they will depolarize immediately. So what we see is we have this rise in voltage, and that is due to voltage-gated sodium channels opening and sodium flowing into the cell. So kind of like the neuron again, that's because those sodium channels are opening, making the cell more positive, and that depolarizes the contractile cell. So what happens after this is a little different, however. Instead of repolarizing, we have a small, little tiny dip, but then we hit this plateau. So here, this isn't important to know, but this small dip is just caused by a little bit of potassium leaking out. But what's important to know is we hit this plateau. And this is called the calcium plateau, and it's due to calcium influx. So normally at this point, we're used to seeing calcium channels close, potassium channels open, but here we kind of have potassium channels or calcium channels open, which lets that calcium flow in, keeping that voltage even. So we haven't learned about this in lecture yet, but we will either on Thursday or next week. But this is kind of due to an increase in permeability to calcium and a decreased permeability to potassium. So we haven't hit that hard in lecture yet, so I'm not going to go too in depth with that, but that is what's kind of going on here. But again, this is called the potassium or the calcium plateau. We'll have the depolarization, then the plateau. Calcium comes in and maintains that positive charge. But yeah, so after plateauing for a little bit, we will then have that repolarization due to voltage-gated potassium channels opening and potassium flowing out. So kind of the same thing here. So everything on this is kind of similar to how the neuron works, except for this plateau right here. So why this plateau happens is because normally an action potential we saw lasted from about 0 to 20 milliseconds. However, I don't have it labeled on the x-axis, but this is looking at 0 to 200 milliseconds. So a lot longer than a normal action potential. So this would be about 200 milliseconds. And we need that plateau for the reason of letting that cardiac cell relax, kind of have this refractive period. So this calcium plateau, think of it as a protective mechanism. Think of the calcium plateau as a protective mechanism because it's going to prolong the refractory period for the cardiac contractile cells and prevent cramps. So if you are like, overdoing your skeletal muscles, they'll begin to cramp up. But we have control of our skeletal muscles. So when we cramp, we can kind of like take a break. We don't have control over our cardiac cells. It's not like we sit here and think, okay, beat, like it does it involuntarily. So they need some type of natural protective mechanism to make sure that cramp doesn't happen and prevent that cardiac muscle tetanus. Tetanus is a cramp. I don't know if y'all ever took like an anatomy class, but back in my anatomy lab I would teach, we had this electrode that we could put on the brachial nerve and it would stimulate like a twitch in your hand. And as we increase the voltage, your hand would start going more and more. And then it gets to the point where your hand went like that. And that's what tetanus is called. Like whenever you like cramp up and your muscles are completely contracted, that's what we're trying to prevent. We're trying to prevent cardiac muscle tetanus because of course we want it to relax and have time in between. So yeah. All right. Exactly. Charlie horses of the heart. Definitely don't want that to happen. Yes. All right, cool. So now we are actually hopping into the discussion worksheet. So question number 1, we're going to draw a flow chart illustrating the normal impulse conduction through the heart, and then we're going to look at how depolarization is conveyed. So this is what we're doing. We're drawing out an ECG or EKG, an electrocardiogram graph. So this is what they kind of look like, and this is definitely spread out, so we can label it. Normally it would be a lot closer together, and we'll see pictures of that a little bit. But starting us off, we're going to spread it on out. So let's go ahead and just first discuss what it is. Again, ECG is looking at the electrical events of the cardiac cycle. When I say electrical events, I mean depolarization and repolarization. So we're looking at the depolarization and repolarization stages for the atrium and the ventricles. So let's start labeling these. So first we have the P wave, and this is showing us atrial depolarization occurring in the essay note. So atrial depolarization. Think of depolarization and contraction as the same thing. So the atrium depolarize, the atrium contract. Next, we have the QRS complex. So you don't need to know this, but this is Q, R, and S. So Q is the point right here, R is the point right here, S is the point right here. You don't need to distinguish between those, so don't study that too hard, but just in case you were wondering. And what the QRS complex is showing us is ventricular depolarization. So right here is when the ventricles contract. And again, the ventricles need a lot stronger of a contraction than the atrium. That's why that point is a lot higher. This is also showing us atrial repolarization. So we also have the atrium repolarizing or relaxing. So depolarization, contract, repolarization, relax. So there's kind of like a double thing going on here. Atrial relaxation, ventricular contraction. And this is kind of occurring at the AV node. Lastly, we have the T wave, and this is showing us ventricular repolarization. So the ventricles relaxing. So these are the major points. However, we also can break it down into segments and intervals. So this line right here between the two waves is called the PR segment. Again, showing us atrial contraction. So in this time, the atrium are contracting. We also have the ST segment. This is ventricle contraction. So between here and here, the ventricles are contracting and the atrium are relaxing. So segments are just looking at the lines. The intervals include the waves. So first we have the PR interval, and it includes the P wave all the way to the beginning of Q. Then we have the QT interval. So from the Q wave to the beginning of the T wave. You might also hear like the R to R interval, like from R all the way through back over to R, or the P to P interval, you know, P right here all the way through back over to P. So intervals include waves, segments do not. Segments just look at the action going on between the waves.
So I'm just wanted to clarify.
Yeah.
So the waves is when it depolarizes, but so that's not like depolarization causes contraction or is contraction?
It causes contraction.
Okay.
Yes. So this is going to be like whenever it's getting ready to contract, and then here we're going to have the actual contraction.
And then when it goes like QRS, is this depolarization and that
yes.
depolarization?
So
I'm just confused.
yeah.
Is that first part hyperpolarization?
Yeah, I don't know what this first part is. I don't know what the Q is, but I know the R is the ventricular depolarization. So when it's getting ready to contract, and I believe this is the atrial repolarization, but it could be that as well. So I'm not super sure. We didn't discuss that. And I know he said the QRS is not important to know the specific things going on, but this is definitely the ventricular depolarization here, the R wave, but I'm not sure which one's atrial repolarization. But yeah, good question. Anyone else? Awesome. Okay, so these are like the important things that you need to know in regards to the EKG and labeling it. Oh, in ventricular relaxation there. So something important to keep in mind, and my Zoom is in the way. Let's see. Grab it. How do I grab it? It like came off of my laptop screen and went over to the computer screen. That's so weird. Okay. Ooh. Okay, so something important to remember is that electrical events will always precede the mechanical events. Depolarization will cause contraction, repolarize, relax, repeat. So depolarize, contract, repolarize, relax. So, you know, again, depolarize, contract, repolarize, relax, you know, so that is just something important to remember. All right, cool. So I'm not going to go over this, but I just wanted to put it in here in case you wanted to look at it later. It's a really good illustration of kind of what's going on, you know, with those P, QRS, you know, T wave and all of that. So this is good if you're still kind of a little lost on what's going on during the cardiac cycle when looking at an EKG. So feel free to reference this on your own time. All right, so now we're going to hop into question 2. It's a pretty loaded question. So we're looking at a normal EKG. So like what a regular EKG looks like. We're going to label it. We're going to calculate heart rate. We're going to kind of just not even discuss, but just know where to analyze these 4 different things. And then we'll look at where that ventricular sodium influx occurs. So let's break it down one by one. So this is the labeling part. So I'm pretty sure after what we just did, this is going to be pretty easy. So the QRS complex, is it A, B, or C? A, B, or C? The QRS. Here, here, or here? Yeah. So the QRS complex is those points representing that ventricular contraction, so those high points. The P waves are these little guys right here before the QRS complex. So P waves always come before the QRS complex, and the T waves follow the QRS complex. So this is kind of the labeling of a normal EKG. So now looking at calculating heart rate, we are able to do that because these intervals are even. They're pretty stable. So how we would calculate heart rate here is looking at our time and how many QRS complexes we have. So in looking at this 3 seconds here, we have 1, 2, 3, 4 QRS complexes. So that means 4 beats. We divide it by the time, 3 seconds, and then multiply it by 60 seconds. So seconds will cross out, and what we will be left with is 80 beats per minute. So 80 beats per minute. So that's how you calculate heart rate when looking at an EKG. There will be some type of time segment given, and you will look at the QRS complexes, divide it by the time, and then multiply it by 1 minute or 60 seconds to get your overall heart rate. So you don't do heart rate in seconds per minute, you do it in beats per minute. Or sorry, beats per second, you do it in beats per minute. So make sure when you do that math that those seconds cross out and you're left with beats per minute. All right, any questions on that part? Oh, cool. All right, so this is kind of just gonna be memorization. So there's not any great explanation here. But we're gonna look at which wave or segment or interval we would use to determine these 4 things. So when determining the AV node electrical activity, that's gonna be that PR segment. So from P to R, again, the R wave is the top of the QRS complex. That's gonna show us what's going on electrically in the AV node. When looking at atrial rhythm, we're going to look from the P interval to the next P interval. So an entire interval or just the pattern of P waves. And that's going to show us, the rhythm. When looking at conduction through the ventricular muscle, this is the QRS complex. If conduction is abnormal, the shape is going to change. And we'll see an example of that coming up in a little bit. And then lastly, the refractory period of contractile action potentials, that's going to be that ST interval or the QT interval. So that's kind of looking at that calcium plateau. So this is something to kind of just memorize, and then you can look at the things we've drawn out so far and try to make it click in your head of, okay, yeah, that would make sense why that's how we analyze AV node electricity or the refractory period. So just kind of compare this with the charts that we've drawn to kind of make it click. Cool. All right. Do y'all know what event they're setting up for outside? Looks like a pretty big deal. All righty. Okay, so moving on to D. So in which part of the EKG does the ventricular sodium influx occur? So we can think back to this and this example that we did earlier. So that ventricular sodium influx, so that's happening right here. We know that is depolarization. So when the ventricles depolarize, that's happening right here at the R wave. So at the R wave is where we see the ventricular depolarization, also known as ventricular sodium influx, and ventricular contraction. So there's a couple different ways to, talk about the same thing here. So, know that for ventricles contracting, we can call that ventricular depolarization. We can call that sodium influx. There's a couple different, terms that we can use for all of these different sections. So make sure you're comfortable with that, because you might know, okay, ventricular depolarization, but Dr. Chang on the exam might use ventricular sodium influx. So just make sure for all of these sections, you can compare, influx, depolarization, and contraction. Same with the atrium. So atrium contraction, is going to be atrium depolarization and be able to, pair it up on the chart with what's happening there. Okay, cool. The answer here is during the R wave. All right, so question number 3. How would the trace in number 2 change under sympathetic influence on the pacemaker cells? This is our normal EKG for number 2. However, when we look at an EKG with increased SNS activity, what's going to happen is those R to R intervals are going to get a lot closer together. They're going to kind of decrease the R to R interval. So R to R interval is looking from here to here. So R to R. So when we have increased SNS activity, increased fight or flight activity, the heart rate is going to increase and those R to R intervals will decrease and get a lot closer together. We'll have a lot faster of a heart rate. So here we calculated that as 4 beats per 3 seconds. Here it would be like 1, 2, 3, 4, 5, 6, 7, 8 beats per 3 seconds. So if you did the math there, it would be a lot bigger of a heart rate. All right, so why does this occur? So sympathetic activity is caused, of course, by the release of adrenaline. And if you remember from last unit, adrenaline binds to those beta-1 receptors on the SA and AV node cells. This will increase CAMP, which will result in increased funny channel openings and calcium channel activity. So remember that IF is those funny channels opening. So that's sodium and potassium is kind of coming in. And then when that calcium channel opens, we have that fast depolarization. And so, yeah. Okay, cool. Give y'all a second to write. So those are the funny channels. So looking back to
RBI and
which one?
yeah.
Oh, beta-1 receptors?
Oh, wait, one.
Yeah, sorry. Yeah, beta-1, sorry. I could not find the Greek symbol for beta. But yeah, beta-1. Okay, cool. Alrighty, so moving on. So question number 4, can we accurately determine heart rate in the recording below, and which problem does, or which pacemaker does the problem originate? So looking at this, I don't know what you call this, a strip, or I think it's called a strip, an EKG strip. Can we accurately determine heart rate? Does anyone know the answer? Exactly. No, we cannot, because the interval is constantly changing. Unless we have stable, R to R, we cannot determine it. It has to be stable, because we would get very different calculations if we look from here to like here. We'd get a very different number if we calculated here to here. So whenever those intervals are constantly changing, we cannot accurately determine heart rate. And when we are trying to determine which pacemaker this problem is going to originate, SA node, because we know the SA node is the pacemaker that determines rhythm. So it determines the interval's stability or constantness. I don't know if that's a word, but the SA node, will make those intervals constant if it's functioning correctly. If the SA node is not functioning correctly and we're having a problem with it, our strip is going to look something like that, not constant intervals. So we can call this sinus arrhythmia. So heart rate, and hang on, I wrote a note about that earlier. Let me see what I said about that. Normal heart rate is sometimes called normal sinus rhythm. So heart rate and sinus rhythm are kind of synonymous. So my note here was sinus, you can think heart rate. So heart rate arrhythmia. irregular rhythm of heart rate. So, we see the P wave, but it's not lining up with the intervals. So this can be sometimes considered normal if like you're breathing a lot harder. So if you're like running up a hill and then going flat and then like running down some stairs, this can be, normal if you immediately took an EKG. But if you're sitting there at rest and this is occurring, that's definitely not going to be considered normal. It will be considered pathological. So if you're sitting there at rest and your breathing pattern isn't changing a lot, then that would be considered pathological. However, if you're like, running across campus, going up different, inclines and different speeds, then this could definitely be considered normal. But that's all going to be due to how you're breathing. So if you're breathing normally, this should not occur. But if you're having changes in respiration, this is somewhat normal. All right, cool. Any questions? All right, question number 5. So here we're going to look at a strip that's showing us some common pathology. Pathology means like a common disease or condition. So we're going to look at which condition is present in both traces. We're going to look at what the condition is called, and then the difference between A and B. So let's hop on into it. So here are our 2 strips. And what we see is the first strip is showing us first degree heart block. So first degree heart block, it's going to be a lot more important, however, for you to know partial heart block. So you don't need to really know first degree, know partial heart block. So what we see going on here is that only the PR segment is lengthened. This is really common when looking at conduction disturbances, and it can occur in both healthy and diseased hearts. So let's see, here's our P wave. It's so hard to read when they're upside down like this. And again, Dr. Chang said the shape doesn't matter. So you're gonna wanna focus more on intervals. So from like here to here, here to here. So don't worry that this is like inverted or anything. In this class, we just need to worry about the intervals because that's showing us kind of the physiological things going on. So if you look at the PR segment, let's see. So that's T, here's P. You can see it's pretty lengthened compared to how these are. Hard to explain. But what happens in a partial heart block is the PR segment is lengthened. So this is going to be due to delayed AV node signaling. So you can think of like traffic on I-35, there's a delay, but you can still get through. So, there's a partial block. So you're going to be in traffic, but you can still get through. Compared to this one, we have a complete heart block. So a complete heart block. And what's going on here is our QRS is completely dissociated from our P wave. So our ventricles are beating very slowly. I mean, these are super spread out. And that's just due to that rate set by the Purkinje fibers. But this is kind of going to be a full closure. So like if an 18-wheeler flipped across the entire highway, there's going to be like no really getting through. We're going to have these super slow beats. The P wave, is completely dissociated from the QRS. I mean, it's different in each one of these. I mean, here it's super close, super far, medium far. Here we have 2 P waves, a TP, P, it's a complete block. So a lot of issues going on there. And a way that you can, see this is if Dr. Chang puts this on an exam, just if there are multiple P waves before the QRS complex, that's going to tell you it's a complete heart block. So multiple or more P waves, than QRS complex is definitely going to show us a heart block. And then lengthened PR segments is going to show us the partial. All right, cool. 41. I got 5 minutes to get through this. Okay, so now we're going to look at VFib and AFib and their distinguishing factors and which one is more serious. So this is showing us atrial fibrillation, and this is showing us ventricular fibrillation. So they look totally different. So what we see is that atrial fibrillation occurs when the atrial cells do not fire synchronously. There's no obvious like P wave. It's pretty, here you can't see one much at all. Here it's like, is that one? Is that one? This isn't as serious as ventricular fibrillation because 80% of the blood can still be passively sent to the ventricles due to gravity. So we don't have to have a contraction to get all that blood to the ventricles because gravity will do that for us. Ventricular, and just, I forgot to mention this, fibrillation is when the heart muscles do not fire together. So that's what fibrillation as a whole means. Those heart muscles are not firing together. But when we see ventricular fibrillation, of course, those ventricular cells are not firing synchronously. And this is very serious. This is when you would need to use a defibrillator and shock someone to get their heart to, re-rhythmize or like get on, the steady pattern. So when we go into ventricular fibrillation, you will have zero blood ejection to your body. Atrium send blood to the ventricles, ventricles send blood to the body. So when this occurs, our muscles are not firing together. They're not really working anymore. And no blood is going to get sent to the body. When we get no blood to the body, we get no oxygen to the cells of the body, and our organs and tissues will die. So ventricular fibrillation is very serious, and that's whenever you see like people getting the shock on their heart, like that's us trying to shock the AV node and the SA node to kind of like restart firing together. They're not firing together correctly, resulting in just completely bad rhythm. But yeah, that's all I have today. Finished, let's see, what time is it? 43, cool. All right, so if y'all have any questions, I'll stick around for a couple minutes. If not, y'all are free to go. Peace.